Welcome to episode 6 of the Big Picture Podcast.
This is the episode where we finish up chapter 4 of Conceptual Chemistry.
Quantum mechanics.
Hey.
We're finally here.
Now, don't get too excited. We're not going super deep into this. Hopefully, though, just enough to help you with the big picture.
Any math? How much math are people going to need?
Remember, we're conceptual. We're digging into heavy concepts, that's for sure. But the math, you'll just need to know, like, which is bigger, 3 or 2. You good with that?
Okay, so where do we begin?
Section 4.5, light. We ought to begin by making sure we have a handle on the nature of light. Ready?
Ready.
Light, as it says in the title, is a form of energy. And I think we mentioned this before. There are two things in the universe, matter and energy. And the two are actually interconvertible by Einstein's equation E equals mc squared. I bring this up because that is important to quantum mechanics, as we shall see shortly. But when we talk about light, we're on the side of that equation where it's like pure energy rather than being matter. So energy manifests itself in the form of a wave. And when we're talking about light, what is it exactly that's waving? Turns out what's waving is electric and magnetic fields. Now, I know you understand a magnet. It has a magnetic field around it, and so I like to use that by analogy. Take a magnet and you can envision the field lines surrounding that magnet. Now, quickly flip the magnet, just twist it in your hand, and the field lines are going to follow. If you take that magnet and flip it back and forth, back and forth, back and forth, you'll see those field lines are flipping back and forth, back and forth, back and forth. So by moving the magnet, you can create what are essentially waves in those magnetic fields. Now, when we talk about light, what's moving here is typically the electron. The electron's not very massive. It has a charge. Around that charge is an electric field. Now, as that electron vibrates back and forth, guess what happens to that electric field?
It vibrates back and forth.
As well, in step with how the electron is vibrating. From physics, we learn that when you change an electric field, you necessarily generate a little magnetic field. And as that magnetic field is being generated, it actually feeds back to generate the electric field. The electric field and the magnetic fields are intricately entwined. They reinforce each other. And so you can't take an electron and start moving it around without creating these ripples in electric and magnetic fields surrounding that electron. Get that electron moving back and forth like 7 billion times per second. Those ripples in electric and magnetic fields are detected by the retina of your eye. That is the very nature of light. They are ripples in electric magnetic fields. It's a form of energy, and that energy is coming in the form of a wave, reaches our eye, and it tickles the back of our eye. It sends a signal through our optic nerve to our brain, and we go, I see. So there's your quick description of electromagnetic radiation. You understand it's called electromagnetic because it involves electric and magnetic fields. It's called radiation because it radiates outward from the source of vibration, say an electron. It might be an electron that's vibrating. Now, we have the electromagnetic spectrum. You can have the electron moving back relatively slowly at only like 100 or 1,000 times per second, and you generate what are called radio waves. Make it vibrate back and forth faster, 10 to the 8th hertz, and you have microwaves even faster. You end up with infrared, and 4 times 10 to the 14th hertz cycles per second. You're there now in visible light. Beyond visible light, you have ultraviolet, then you have X-rays, and you have gamma. The point is, they are all the same thing. Radio waves, microwaves, infrared light, ultralight, gamma, and X-rays are all forms of the same thing that we call electromagnetic radiation. And put them all together and you have what's called the electromagnetic spectrum. 4.6, atomic spectra, and the quantum hypothesis. Now that we have a bit of understanding on the nature of light, different colors are merely different frequencies of electromagnetic radiation, we can start applying this to the world of atoms and molecules. Let's introduce what we call the spectroscope. The spectroscope, what it does is it simply passes light through what's essentially a prism. Technically, it's a diffraction grating, and it splits light into its component colors. It shows you a rainbow of light. White light turns out to be the combination of RGB, red, green, and blue all together. And so you take that white light and pass it through a prism or diffraction grating, and it will separate it into its color components. You'll see the rainbow of colors. Now, that's what a spectroscope does. It just splits the light that you're looking at into its color components. What happened here is they started looking at elements that were being heated. They were looking at the light from that process through the spectroscope, and they were finding something quite bizarre. Each element emitted not every frequency of light. An element would emit only particular frequencies of light.
You mean like a fingerprint?
Exactly. If you look at strontium through the spectroscope, you'll see a certain pattern of lines, and that will be different from if you're looking at, say, barium through the spectroscope. Now, what we're talking about here are the atoms of particular elements. When you heat them up, sure enough, the electrons of those atoms are vibrating and they generate light. The deal is this: each element emits a particular pattern of light. The question was this: why?
Because they're different elements. They have different fingerprints.
It's their identity. So you can look at your fingerprint and see, well, we're different by the patterns. But why are they different like that? And to get to that why, you're going to need to go down to the level of the DNA, right? What's behind it? And so likewise, they're looking at this atomic spectra. They're saying, what's behind it? Why is it that strontium looks like that and barium looks like this? From the study of atomic spectra, particularly the spectra of hydrogen, the simplest of all, came the idea from Niels Bohr of what we call the quantum hypothesis. Now, you understand people are having a hard time believing that matter was made out of these particles rather than being continuous, like a pudding or something. Well, when you have matter made out of particles, really what you're talking about is matter being quantized. Quantized, that means it comes in discrete quantities, like steps on a staircase, as opposed to a ramp. A ramp would be a smooth and continuous way of getting upstairs. So looking at the particulate nature of matter, we see that it's quantized, and that took some time before we really began to embrace that model of the nature of matter, the ideas of atoms. So in a way, you're already familiar with the idea of the quantum, because we've talked about atoms and particles already, down to subatomic particles even. What's different here is that Niels Bohr is talking about not just matter being quantized, but, drumroll, energy itself being quantized. So he proposed this. Within an atom, you have what he called, for lack of a better word at the time, orbits. And an electron in a higher orbit would fall down to a lower orbit. And when it did so, it's losing energy because you're going downhill. You're getting closer to the nucleus. You're an electron and you're going to a lower orbit. You're going downhill effectively because you're getting closer to where you want to be. When you do that, you're losing energy, and the energy is lost in the form of light being emitted by that particular atom. He was proposing the DNA behind why it is that different elements have different fingerprints. He was saying that, well, the electrons are going around this thing called the nucleus. Maybe the electrons are held to these different orbits. And so when we're looking at the fingerprint of an element, we're really looking at the pattern of orbits within that atom. As an electron falls from a higher orbit to a lower orbit, you might be thinking like a squirrel jumping from a higher branch to a lower branch. That's not what he was proposing at all. He was proposing that energy itself is quantized so that there's nowhere in between. It's like the steps on a staircase. Put your seatbelt on. That electron going from the higher to lower orbit doesn't travel from the higher to lower orbit. It flips boop, boop, like a light switch. It's either there or it's here, and it's never in between. Just as the bizarreness of having space, a vacuum of space in between different particles is the oddity of the particulate nature of matter, this is the oddity of the particulate nature of energy itself. It's called quantum theory. Now, theory means a well-tested explanation of the nature of the universe. And quantum theory has been confirmed over and over again, just as the theory of gravity. I don't want any hesitation when you hear this idea of quantum theory. That elevates its status. Quantum theory is here to stay. It's something we need to work with. Scientists do on a daily basis in their considerations. It's a worldview, if you will, that's beyond what we normally see. But down at the world of atoms and their subatomic particles, this idea that energy is quantized is everything. It dictates the behavior of those atoms. And again, remember, we're talking about conceptual models here. We want to be able to predict the behavior of those atoms. Quantum mechanics is the way to do that. So if you really want to know about what's going on there, you need to learn more about this thing called quantum mechanics. And you can bet it goes into lots of detail. We don't need to do that here to get to the gist in terms of how it is that atoms and molecules behave. So we're going to skim over a lot of it, but we want to give you the higher level, big picture stuff relative to quantum mechanics.
Okay, so quantum mechanics. It goes from a higher state to a lower state.
Yeah.
And during that process, it goes from one to the other without at any point being in between the two.
Absolutely.
So that is what is quantized.
That's the bizarreness of quantum mechanics, is that there's nowhere in between. It's truly the steps. You can have an electron there or an electron here.
So it's just like how I think about I might want one thing 1 minute and I want something else the next.
Yeah, it's A or B. There's what's in between A and B.
There was no process.
Hey, our alphabet is quantized. That's a fun thing to do, to think about what's quantized. Money is quantized. The smallest unit is a penny, at least in U.S. currency. Lots of things are quantized, including energy. So when an electron jumps from a higher energy state to a lower energy state, it emits light. When it's absorbing light, that energy of the light lifts the electron from a lower state to a higher state.
And the higher states are further away from the nucleus?
Yeah, think of it in terms of gravity. You know, the higher you go up a ladder, the more potential energy you have, the more it's going to hurt if you were to jump off that ladder. Likewise for the electron, it's negative, the nucleus is positive, there's an attraction between the two. So as you pull the electron away from the nucleus, that takes energy to actually pull the electron away from the nucleus. And conversely, when the electron falls down toward the nucleus, that's the opposite. It's like falling down the ladder. Energy is released. The energy here is a form of kinetic energy, to be sure, but it's electromagnetic radiation. which happens to be a form of kinetic energy, FYI. So the electron shifts, I don't want to say falls, shifts from a higher state to a lower state, bam, light is emitted. And how far of a jump that is determines the frequency of the light that is emitted. If it's falling pretty darn far, it's going to be a higher frequency. If it's not so high of a jump, it's going to be a lower frequency. So that's how it is. The spectra of different elements, the patterns, the fingerprints that you're seeing there are indicative of these quantum states within the atom. If this isn't trippy enough, it's time to go over the edge. You're probably thinking of an electron as a tiny particle.
Yes, a tiny particle.
Okay, it turns out it also exhibits properties of a wave.
It can do both a particle and a wave.
That means, you see, it's manifesting itself as a form of matter, yes, but it's also a form of energy.
And this is different than like matter having energy?
Matter and energy are actually the same thing, just different manifestations of that same thing. It's like one mouth that can both smile and frown, but get this, at the same time.
Wow, okay.
So think of that electron as a condensed bit of energy, or as a condensed packet of energy.
Okay, that makes sense.
And you'll begin to understand why the electron is restricted to particular energy states. Here, listen to this whistle. You ready? Just the continuous sound from a high pitch to a low pitch.
Okay.
And now what I'm going to do is I'm going to do that same whistle down a tube. So we have a tube here in the studio. Okay, you ready?
Okay, ready? All right, I hear the same sound going down, the pitch going down. What am I listening for? Can you help me?
Listen to the steps. Here's without the tube. Here's with.
Okay, so rather than being smooth all the way down, there's little gaps. It's like a little bit choppy. Is that what you mean?
Choppy, yeah.
Okay.
Yeah. What we're finding is that when you confine the whistle to the tube, you're quantizing the whistle.
Okay, can you do that one more time now that I know what I think I know what I'm listening for.
Okay, here's without the tube. Here's with the tube.
Wow, okay, I heard that.
Yeah, so with the tube, you have actually quantized your whistle. So confine the whistle to the tube and it's quantized. You'll hear it's quantized.
Okay, so when you say we're hearing it quantized, we hear it in one tone and then there's nothing for a second and then we hear it in another
Essentially,
tone?
yeah, there's steps.
Okay.
There's steps. So here's the deal. Likewise, confine an electron wave to an atom, and you get the same result. Only certain wave frequencies are permitted, and bam.
Oh, so there'll be gaps in certain places.
You've got the quantization. You've got Niels Bohr's quantized states. You've got atomic spectra, those fingerprints.
Oh, I think I get it.
Underlying it all is the electron having these wave properties. And if it has a wave property, that means you can have steps like a whistle down a tube.
So when you say an element has a fingerprint, what we're seeing from the light spectra is certain colors or certain, what we were hearing as tones, now we're going to see as certain frequencies of light.
Discrete frequencies like 451, 492, nothing in between.
Right, okay. And each element will have its own particular pattern of those frequencies.
Exactly, because In one atom, it's like you're whistling down a long tube. Another atom, you're whistling down a shorter tube. You have a bassoon, you have a flute, you have a French horn. All different characteristics with different tones, if you will.
That's awesome. That's really helpful.
Okay, great. That's section 4 point whatever. All right, so these electrons are restricted to these particular orbits, or let's say states, within the atom. What do those states actually look like? You might be tempted to be thinking of a planet going around the sun. That's not bad, but it's not quite accurate. How the electron spends its time in a particular state is spelled out by what we call an atomic orbital. Now, an orbital is a waveform. It's like a cloud. It's three-dimensional. It's mathematical, very much so. Remember, we're glossing over a lot of this. At its core, the orbital defines where an electron is 90% of the time when it's in a particular state of energy. And you can have orbitals that are spherical. It's fairly easy to understand, but do the math and you'll find they're actually orbitals that look like dumbbells. They're orbitals that look like balloons, funny shapes. Watch the videos at Conceptual Academy and you'll see where we display a number of these bizarre looking shapes. But what you're looking at when you're looking at an atomic orbital is the three-dimensional wave of an electron at a particular energy level. I think that's enough to say about atomic orbitals. If you go into general chemistry and beyond, you'll be digging much deeper into why they look like that. And you know what? We're even going to move past on energy diagrams for the multi-electron atom. I don't personally teach this in my own course, and I think for subsequent edition, you might not even see the electron configurations shown here. What am I talking about? The 1s2, 2s1, 2p6. It's common material used in Gen Chem. If you're advancing further into chemistry, be sure to look over this section on how it is atomic orbitals can get filled based upon their energy levels. But for our purposes, I want to just jump straight ahead to what we call the noble gas shell model of the atom. We began this chapter with physical models and conceptual models. This shell model noble gas shell model is a conceptual model that I think really nicely summarizes what we need to know for understanding bonding of atoms into molecules and chemical reactions. Let's dig into that for just a bit here. Imagine an atom like this. At the center you have the atomic nucleus with its protons and neutrons. And surrounding that are a series of concentric shells. Let's say 7 concentric shells. By concentric, I mean they all share the same center, the atomic nucleus. Now, each shell can hold a given number of electrons. Bear in mind, we're glossing over a lot here. A shell, technically speaking, is a combination of different orbitals of similar energy levels. I know, don't worry about it. But the first shell, because of the orbitals it represents, is allowed to hold 2 electrons. It's the shell that's closest to the nucleus, which, frankly, electrons like. Now, the second shell, it can hold 8 electrons. And then beyond that, it's the third shell. It too can hold 8 electrons. The fourth shell, it can hold 18. The fifth, 18. The sixth, 32. The seventh, 32. Why those numbers? 2, 8, 8, 18, 18, 32, 32. It has everything to do with the number of atomic orbitals that make up that shell. And it also has everything to do with the universe into which we were born into. In another universe with different constants, different physical laws, you might have different numbers of electrons that can fit into the shells. But for where we live, the numbers are 2, 8, 8, 18, 18, 32, 32. Those are the number of electrons that can fit within these shells from innermost to outermost. Given that, you can build any atom of the periodic table. And let's keep it simple, starting with
hydrogen.
Hydrogen. A hydrogen atom's got one electron. That electron is going to want to be as close to the nucleus as possible. Why?
Because it's attracted to the positive proton.
Right. Because it's attracted to the positive proton in the nucleus. So there you have it, a hydrogen atom.
What if there's a neutron in there? Does that cancel out the positive charge?
Nope. The neutron is neutral, so it doesn't play a role. It just is contributing to the mass. What we're talking about here is the electrical attractions between the electron, negatively charged, and the proton in the nucleus, which is positively charged. So let's build a helium atom, shall we? How many protons in the nucleus of a helium atom?
2.
That would mean for a neutral helium atom, you've got 2 electrons. So the first electron's gonna want to go in the first shell. Now add the second electron, where's it gonna go?
There's room for 2, so it stays in the first shell.
You have just built yourself
a helium atom.
A helium atom. So the shell model of the helium atom has the nucleus in the center with a +2 charge, and surrounding that in the first shell are 2 electrons. Now let's move to lithium. Lithium number 3, atomic number 3, has 3 protons. That means for the neutral lithium atom, you've got 3 electrons. How might those electrons be configured in a lithium atom?
That third electron is going to have to go to the next shell.
Why can't we just take that third electron and put it in the first shell? Because that third electron loves the positive charge of the nucleus, doesn't it want to be there?
Of course it does, but based on experiments that have been done, evidence suggests that only 2 electrons can be there.
So in this universe, we find only 2 electrons can reside in that first shell. So that third electron in the lithium atom is forced to reside in the second shell. So let's think about this. The helium atom has 2 electrons, and they're both in the first shell. The lithium atom has 3 electrons. 2 are in the first shell, and 1, the third, is in the second shell. So which is heavier, lithium or helium?
Lithium has more protons and neutrons.
So it's heavier, right? Okay, but let me ask you this. Which might be larger, a helium atom or a lithium atom?
The lithium atom has another shell, so the electron is spinning around farther out from the nucleus, so it's bigger.
It's sweeping out a greater volume of space. That third electron is.
Yes.
While the nucleons define pretty much the mass of an atom, what defines the size of an atom? That's the role of the electrons. Let's do a couple more. So we went from hydrogen to helium to lithium. Let's do beryllium now. Beryllium has an atomic number of 4, so it's got 4 protons. Let's see how the electrons fill up the beryllium atom. Go ahead.
2 electrons can be in the first shell, and the second 2 electrons can be in the second shell.
So beryllium has 4 electrons. 2 are going to be in the first shell. The remaining 2, the third and fourth, are going to be in the second shell. Now, that second shell can hold how many electrons?
8.
8, all right? So we still have plenty of room in that second shell, right? So envision the first shell is filled for the beryllium, but the second shell has 2 electrons in it, and there's still room for 6 more. Here's the question. Which might be larger, a lithium atom or a beryllium atom?
Well, they both have 2 outer shells.
They both have 2 shells with electrons in them. The lithium has 1 electron in the second shell. The beryllium has 2 electrons in the second shell.
How many protons are there?
In lithium, there are 3 protons. In beryllium, there are 4.
So I'd say they're the same size.
let's look at the forces here. How do you suppose electrons feel about electrons?
They're the same charge, so they would repel each other.
They don't really like each other. So they want to spread apart away from each other as much as possible. So that's one thing to think about. Here's the other thing to think about. How do electrons feel about the atomic nucleus?
Quite attracted to those protons.
Why?
Because it's a positive charge attracting a negative charge of the electron.
Because of the electromagnetic force, whatever that is. It's actually one of the fundamental forces in the universe. And we're using that, we're invoking the electromagnetic force here to explain how it is that an electron likes the nucleus. The electron's negative, the nucleus is positive, right?
Right.
Now I want you to put yourself in the point of view of one of those electrons in the second shell. Are you there?
Mm-hmm.
What do you see?
Well, sometimes I see the nucleus, the atomic nucleus.
Yeah.
But sometimes those other electron orbitals are blocking my way.
Now, when you look down to the nucleus from that second shell, would you agree there's the first shell that's in between you and that nucleus?
Yes.
Aha. Okay, so what's the charge on that first shell?
-2.
There are 2 electrons there, are there not?
There are 2.
And how do you feel about that? There you are, an electron in the second shell, looking downward toward the nucleus, which you love, but in the way you see 2 electrons. Yum, yum, or yuck, yuck.
Yuck, yuck. It's like tall people sitting with hats in front of you at a movie theater.
Yeah, excellent. All right. You want to see the screen, the nucleus, but people are in the way. All right, let's quantify this a little bit, shall we? How many electrons are pushing you away from that nucleus?
2.
So there you are, an electron in a lithium atom, and you're in the second shell, and you look to the nucleus, and there are 2 electrons in that first shell, and they're pushing you away. So that's a -2, pushing you away. But what's there in the sweet nucleus?
Those beautiful protons.
How many?
I forgot.
We're in a lithium atom.
Okay, 3.
3. So you look at the periodic table and you see the atomic number of lithium is 3. So there are 3 protons. Which is bigger, 3 or 2?
3.
3. All right. So there you are, that electron, and you see a +3 pulling you into the nucleus, but you see -2 pushing you away from the nucleus. Who wins?
The +3.
Yeah. So you're held there by the nuclear charge of +1. I know the real nuclear charge is 3, but from your point of view, the effective nuclear charge, the reality of it from your point of view,
As an electron.
out there in the second shell, you're seeing a +1 because there's -2 pushing you out and there's a +3 pulling you in. Net +1. So you're held there because +1's better than none, right?
Mm-hmm.
All right, now let's do the same game with not a lithium atom, but a beryllium atom.
Okay, +4, 4 protons.
Now there are 4 protons. 4 protons in the nucleus. And you are one of those electrons in the second shell. And you look toward that nucleus. What do you see?
There are 2 electrons in that first shell.
Those pesky 2 electrons in your way. All right? So what's the net result?
The net result, so if there's 2 electrons in the way, but there's 4 protons that I want to get to, or that I'm attracted to as an electron, then it's a +2.
So the effective nuclear charge that you see from your vantage as the second electron in the second shell of a beryllium atom is +2.
Okay, so I'm only being blocked by 2 still.
But there's a +4 there, and so the net result is there's an effective nuclear charge of +2. So let's compare that to what we had before with lithium. That electron in the second shell looks down and sees a +1. Now we're in a beryllium. That second electron looks down and sees a +2.
2.
Which is bigger, 1 or 2?
2, so it has a stronger a stronger pull toward the center nucleus.
Excellent. Exactly. That's it. Bingo. So those electrons in the second shell of beryllium are pulled in tighter toward that nucleus. Why? Because that's got effectively twice the charge. And let's face it, your electrons, you like positive charge. The more the positive charge, the more the atom's going to contract. The more those electrons are pulled inward. And that's why when you're asked which is larger, a lithium atom or a beryllium atom, your answer is...
The lithium atom is larger.
Yeah. Beryllium atom is smaller because they're experiencing a greater what we call effective nuclear charge. And you can go from beryllium to boron, which is number 5, and you'll see the effective nuclear charge jumps to +3. And then to next elements, +5, +8, just it's bigger and bigger. And so as you move from left to right across the periodic table, you're going to find the atoms get smaller and smaller and smaller.
Because the effective nuclear charge gets larger and larger and larger. Yeah, bigger and bigger.
But there's a limit now, isn't there? What's that limit for the second shell?
Is 8 electrons.
Only 8 electrons can be there. And by the time you get to the far right side of the periodic table, you are now at the neon atom, right? Neon has an atomic number of 10. Guess how many protons are in the nucleus of a neon atom?
10.
Yeah, excellent. Then the first shell has how many electrons?
2.
And the second shell can hold how many electrons?
8.
8. And neon has a total of 10 electrons. 2 are in the first shell. 8 are in the second shell. That second shell is filled to capacity. And the neon atom is pretty small. Let's go from neon to sodium. Sodium is number 11 in the periodic table. So where's that 11th electron go?
Well, the first 2 are in the first shell. The second 8 are in the second shell. So that's 2 plus 8 is 10. And then we need one more because sodium is 11 protons.
Therefore 11 electrons.
So it has to go in a third shell.
So which is larger, a sodium atom or a neon atom?
The sodium atom.
Why?
Because it's got now a third shell. So that means the outermost electron is sweeping across a larger area or a larger volume of space.
So that's the key right there, is that when you went from neon to sodium, suddenly you went one shell larger. And that's a jump in size, a quick jump in size. So you'll find that the sodium atom is markedly larger than the neon atom. But notice also something we pointed out here, you pointed out here, that its effective nuclear charge is +1. Didn't we hear that before? That was with the
lithium.
Lithium. That also had an effective nuclear charge of +1. And we can wrap it all up right now. Look to the periodic table. Atoms above and below one another in the periodic table have pretty much the same effective nuclear charge. What you'll find is as you move from the top to the bottom on an atomic group, the atoms get larger. Why?
Because they keep adding shells.
There are more shells. So there are 3 shells in sodium with electrons filled, but for lithium there are only 2 shells. For hydrogen it's only 1 shell. So atoms of elements above and below one another in the periodic table, they'll have similar effective nuclear charges, which is actually why they have similar chemical properties and physical properties. But they're not exactly the same because the atoms get bigger as you go down the group. Why do they get bigger? Because there are more successive shells of electrons as you go down a group. And as you move from left to right across the periodic table, you'll find the atoms tend to contract because of the effective nuclear charge. Put that all together, you'll find your largest atoms are to the lower left of the periodic table, and your smallest atoms are to the upper right. All explained by this idea we call the shell model. That's the essence of section 4.9. And that's the grand conclusion of chapter 4. In Chapter 6, we'll be digging into a shortened version of this shell model called electron dot diagrams. Simplified even further, but very useful in terms of understanding the nature of chemical bonding. To wrap up, remember, there are physical models and there are conceptual models. A conceptual model describes the behavior of a system. Now, the system we're talking about here with atoms are a group of subatomic particles held tightly together in a very, very, very small region of space. So small that we enter a realm where quantum mechanics comes to play. And within those rules of quantum mechanics, we find that electrons can have only particular amounts of energy. And as a consequence of that, electrons organize themselves within these shells about the atomic nucleus. Remarkable stuff.
Hey, so how is the weather connected with an atom?
They both can be predicted using conceptual
models.
Yay! Okay. All right, so next chapter we'll be digging into the atomic nucleus. We have in store a field trip to the Rocky Flats area of Colorado where plutonium was produced for the manufacture of nuclear bombs. We're looking to visit actually a cyclotron in the area where they produce nuclear medicines, talking about all sorts of fun stuff and important stuff when we get to the nuclear chapter coming up next. Our theme music by Zach Jeffrey. Musical flourishes by and in memory of Charles Paxton. For more of his music, look for Charel, that's Char-el, at places such as Spotify. Production assistance from Greg Simmons and C Pro Music. For show notes and more, please visit conceptualscience.com. A note of appreciation to all instructors using Conceptual Academy. Thank you for your support. And to the hardworking student, our thanks to you as well for your learning efforts, which we see as the path to making this world a better place. There's a bigger picture. That's good chemistry. Good chemistry to you.